So one of the reasons we engage in geometric reasoning to begin with is so that we can develop a rule or establish a pattern that we can then describe with an algebra equation or formula. So we can then generalize and apply what we learn from the geometric reasoning. So here is the data table from the interior angles of a polygon filled out. And I just want you to notice or recall that what we did is we drew triangles inside of the shape, and then we know triangles added to 180 degrees. So two triangles fit inside of a quadrilateral, so 180 times 2 gave us the interior angle measure. And that worked just the same with the pentagon. There were 3 triangles that fit inside the pentagon, 4 that fit inside the hexagon, each worth 180 degrees. So we just sum those up to get the interior angle measures. What I want you to notice here is that the number of triangles that fit inside the polygon was always 2 less than the number of sides. So we're going to use that fact to write a better algebra formula than this right here. Here we've got basically the plain spoken English version of how we found the interior angles. We did 180 degrees times the number of triangles that fit inside. But it'd be nice if we could really develop a nice, easy algebra formula here. So your instinct might be to say, well, it was just 180 degrees times n. But n is the number of sides, not the number of triangles that fit inside. And the relationship between those two things was that the number of triangles that fit inside was always 2 less than the number of sides. So what we actually need to multiply 180 by is n minus 2. And so this little formula right here will give us the interior angle measure of any polygon, regardless of how large it is. So we do a 30-sided, 40, 50, 100-sided polygon. And the angle measure would be given to us by this formula down here. As long as we define and accept n here to be the number of sides. And now we're going to use that formula to demonstrate or prove why that the exterior angles always added to 360. So recall, let me get this out of here. Recall that when we did a exterior angle, the way we found that is we said we can extend these lines, and every line adds up to 180 degrees. So what I've really got are a number of 180 degree lines times the number of sides. So it was a 5-sided shape, then it had 5 exterior angles, and we just did 180 degrees times 5, and then we subtracted out the value of all of the little interior pieces right here, because we were only counting the exterior angles, whereas the straight line is sort of counting both the exterior and the interior. So we said we did 180 degrees times the number of sides in the shape, and then we subtracted off whatever the interior angles added up to, and that formula that we just used, we just developed, said the interior is always going to be 180 times n minus 2. So if you distribute this negative 180 to the n and to the negative 2, what you end up with is 180 degrees times n minus 180 degrees times n plus, because negative 180 times negative 2 is 360 degrees. 180n minus 180n is 0. So that cancels out, and all we're left with is that 360 degrees. So this is an example. This is the purpose of geometric reasoning. We do those reasoning activities to develop a formula that we can then use and manipulate algebraically to draw other conclusions or prove the truth of other results.